Hello chemistry students, in this video we're going to be looking at dot point 1.4.2 and 4, and our main focus today will be looking at types of bonding in molecules. We've already looked at some molecules, a fair few, and they've been shown in a number of different representations so far. Some of them show maybe a stick between two atoms, maybe with their symbol or a depiction of an atom. Others might just show that the two atoms are sort of fused together. And all of these involve bonding in some way. Something has to be holding these atoms together to form the molecules, and this is what we're going to be looking at in this video. So first off, there are three main types of bonding. Mostly we look at ionic and covalent, but metallic does exist as well. But first off, ionic, those bonds generally are formed between metal and a non-metal atom. In this instant, electrons are transferred, so one is given to the other. In a covalent bond, we have generally two non-metal atoms bonding together. In this instance, what's happening though is that the electrons are being shared between the two atoms rather than the electrons being completely transferred from one to another. And our last one here, metallic bonds, exist when we have an actual solid piece of metal or a pure metal where there are only metal atoms present. And in this instance, what we say is that the electrons are shared as well, but they're shared in quite a different way in comparison to the covalent bonds. Now I'm going to go through each of these types of bonding and explain how they work. To understand a lot of that though, we need to be looking at our Lewis dot structures. And these exist to help show us how many of the important electrons or the reacting electrons exist in each particular kind of atom. Now, we are going to start looking at this idea of full orbitals when we start talking about the formation of our bonds. But in general, in most cases, what we're looking at are for there to be a full set of s and p orbitals. So that counts up to 8 electrons. So again, generally speaking, if an atom has 8 electrons at the end, or in their outermost orbitals, then it's said to have the most stable electron configuration. So an atom like neon or argon, who naturally have 8 electrons in their final two orbitals, their final p and their final s orbitals, they're stable. They don't really need to react or form bonds with anything else because they have exactly the number of electrons that they want. Something like fluorine, though, for example, only has 7. It's one off from having those 8 electrons that it wishes to have, just like any other atom. Carbon has 4, which means that it needs 4 more electrons. Lithium, though, has only 1, and it's actually easier for the lithium to give away its extra electron or form a bond with it rather than to gain 7 electrons. But that'll make a little bit more sense as we move forward. And you may see these Lewis dot structures showing a depiction of where the electrons are or how many there are as we move along. Now, the first kind of bond that I want to look at are covalent bonds, and this is where electrons are being shared between two atoms. So in this first example that I have here, I have two fluorine atoms, and they both have 7 electrons. In other words, they just need one more electron so that there are 8. So what can happen is that fluorine atoms won't exist naturally by themselves as a single atom. If we have fluorine, the element, they actually come together to form a diatomic particle like the one that's here, so a particle made of 2 atoms. So the atoms will come closer and closer and closer together, and the 2 lone electrons will end up interfacing or interacting with each other. And what ends up happening is that the electrons are shared between the 2 fluorines. So in this case, each fluorine technically has 8 electrons, even though one hasn't claimed an electron over the other. Both of these electrons that sit in the middle belong to both of the fluorines at the same time. So here what we can see is that's been drawn with a stick or a line binding the 2 atoms together. And whenever a line exists between 2 atoms, we say that there are 2 electrons present. So both fluorines will own 6 of its own electrons around the outside, and then the 2 that participate in the covalent bond in the middle make electrons 7 and 8, and that applies for both of the fluorine atoms. In the example down here, I have water. Now, oxygen starts with its 6 electrons, which have been colored in black because it has 6 valence electrons. And the hydrogen only has 1 valent electron that it works with. So what happens is that the oxygen can make bonds with 2 hydrogens, meaning that the electrons are being shared. In this instance, the oxygen, because it's sharing two electrons from 2 separate hydrogens, what it means is it now has 8 electrons in its outer orbitals. The hydrogen, though, doesn't have 8 electrons at the end. It only has 2. It has the electron that it started with and one of the electrons from the oxygen that it has shared with. Now, if we look back at our Lewis diagrams, I've also made a note here in brackets that 1s orbitals that are full are also stable electron configurations. So when we're looking at hydrogen and helium here, they don't actually have to fill up all the way to 8 electrons. They are perfectly capable of just having a full outer shell that is just the 1s orbital, and that's all. That is kind of an exception to the rule, and it only exists for our lightest elements. We also have this guy up here, which is ammonia, which is made of a nitrogen and 3 hydrogens. Now, in this instance, the nitrogen starts with 5 electrons that are colored in black, but we can also use different symbols to represent different electrons, and each hydrogen is bringing 1 extra electron marked as an X to the table. When nitrogen bonds with 3 different hydrogens, it'll end up, instead of having just 5 electrons, it will end up having 8 in total after sharing electrons with 3 other hydrogens. And those hydrogens in turn as well will have 2 electrons on their outer shell as well, and they have a stable 1s orbital too. Now, this isn't the case for every single covalent bond, but this is quite a simplistic way of visualizing how bonds usually form. And they usually form with our p orbitals, or the electrons in the outermost p orbitals. So what you'll see here is that they'll overlap, essentially, meaning that most of the time the electrons that are a part of the bond end up in this merged area where the electrons can exist. So we have one nucleus of an atom over here and another nucleus over here, and most of the area in which the electrons that are a part of the bonding where the 2 p orbitals have overlapped will sort of look like this. Now, there are 2 kinds of covalent molecules that we might see. We might see individual small molecules made of a handful of atoms, but we might also see networks like the ones that we see here, and potentially for some particular elements or compounds, there may be a repeating series of bonds that can form theoretically infinitely over and over and over again to make this network of atoms. We might also call it a lattice. The other kind of main bond that I want to talk about today as well are ionic bonds. And in this, one atom donates electrons and the other accepts. So here I have, for example, sodium chloride that's being formed. The sodium has a single atom that it wants to get rid of. And the chlorine, and that's actually because it has a very low first ionization energy. And the chlorine, which is really electronegative, is quite capable of taking that electron from the sodium. And what that means is, so that first off, the sodium loses its outer electron, and the orbitals that are below it are all full, which means that it's stable. The sodium ends up having a single positive charge. The chlorine has a single negative charge because it's taken 1 extra electron. It has a full and stable set of orbitals as well. Now that it's gotten to 8, it's happy too and has a charge of -1. Story becomes a little bit different though when we have substances that want to get rid of multiple electrons. So here magnesium has 2 electrons that it wants to get rid of. If it was in the presence of chlorine, it would have to give away 1 electron to each of the chlorines present. The magnesium would end up becoming stable because all of the orbitals below it are full, and it has a charge of 2+. And for the chlorines, they both gain 1 electron. They become stable because they have 8 electrons each, and they get a charge of -1. Something else to note that I've got here is that a positive ion is called a cation. So that would be a magnesium cation and a sodium cation. We also have negative ions, and they are known as anions. So our chlorines here would all be known as anions. What we end up forming are ionic networks. We don't end up with small little molecules like we did for covalent substances. Here they always form crystals, so some sort of structure that's repeated over and over and over again, potentially or theoretically infinitely, but what we'll have is the positive ions surrounded by all of the negative ions, which they're attracted to, and the negative ions being surrounded by positive ions, which they are all attracted to as well, and that's sort of what bonds them and holds them together after there's been a transfer of electrons. Now, our last one here is metallic bonding. And it's kind of a mix between covalent bonding and ionic bonding in the sense that it's similar to ionic bonding because all of the metals form cations. They form positive metal ions, but it's not because they've given away their electrons as such. More the electrons are being shared in and amongst all of the positive ions here. So you might hear the term a sea of delocalized electrons, and this is where it becomes a little bit more similar to our covalent molecules because really the electrons are being shared rather than being given or transferred to another atom. Now, these delocalized electrons are free to move about, which is actually why we can form electric currents in metals. We draw them out into a wire and put a positive charge on one side and a negative charge on the other. And all of those electrons will flow and move past all of the metal ions towards where that positive charge has been placed. Now that concludes this video for today. In the next one, we'll start looking at an idea called allotropes. It's sort of related to the bonding stuff that we've been looking at, and it's a small dot point in our syllabus. It's sort of in the same spot. It won't take very long to cover, but until then, have a good one.